A capacitor with capacitance C is in series with a resistor of resistance R and an ideal battery with EMF Capacitor. If the capacitor is initially uncharged, how long does it take to charge the capacitor? How does the current in the circuit vary as a function of time? And how does the potential difference across the capacitor vary as a function of time? We're going to use this example to derive a couple of formulas. Now, I'm going to say this. I'm going to derive these formulas, but I'm not going to hold you accountable for knowing how to derive them. You just will need to know the results of the derivation. But I want to derive them because I know several of you have had differential equations already. And this is a type of problem that differential equations is designed for. We're going to create a very simple differential equation. And if you haven't had differential equations, chances are you will. And differential equations allow us to take equations that are represented by derivatives and solve them. And what we are going to see is these circuits that we are working with, especially RC series circuits, involve derivatives that we need to know how to work with. And these derivatives are going to tell us something about the rate at which charge accumulates on the capacitors of a circuit, or the rate at which it discharges. It tells us something about the current in our circuit, can tell us something about the voltage in our circuit. So again, I'm going to do the derivation. You don't need to know how to derive it, though I'm going to go through it in a detailed way. You do need to know and be able to use the results of the derivation. This example kind of walks us through the derivation. So I'm going to switch to the whiteboard here. And let's begin with the sketch of our RC circuit. So we have a source of EMF. I'll label this as Capacitor. And this will be attached to a resistor and an initially uncharged capacitor. So we will say the initial charge on the capacitor is equal to 0 at time t equals 0 seconds. Some other information, if at time t equals 0 seconds, let's say we then attach this circuit. And let me go ahead and label the resistor's resistance as R. And let's label the capacitor's capacitance as C. And once we connect this circuit, charge will start accumulating on the plate of the capacitor, on both plates of the capacitor. And I'm going to represent that charge as a function of time, Q of t. So when t is equal to 0, we have 0 charge. But after some amount of time, our capacitor is going to be maximally charged with a maximum amount of charge. Our goal on this problem is how long does it take to fully charge the capacitor? So to do that, we're going to need an equation that represents charge and its relationship with time. A good place to start is Kirchhoff's laws. And to apply Kirchhoff's laws, I like to look at various nodes in our circuit. So I'll take 3 nodes between the 3 different components in our circuit, nodes A, B, and C. So if we look at the potential difference from A to B, and let's go ahead and indicate our path of analysis. We're going to analyze in the clockwise direction. I'll list that as 1. And we know that the potential difference across a battery when you analyze from the negative terminal to the positive terminal, that potential difference is equal to the positive EMF of the battery. Let's go ahead and come up with expressions for all the potential differences of all of our components. You're going to see that we're going to need those potential differences when we write Kirchhoff's loop law for voltage. So the potential difference across the resistor. Well, we know the potential difference across the resistor is either a plus current times the resistance or a minus the current times the resistance. Now, what determines whether it's plus or minus is based off of the direction of the current in relation to the direction that we analyze our circuit. So we know that positive current will flow from high potential to low potential. So that would be, if we look at the circuit from the positive terminal of the battery back down to the negative terminal of the battery. So our current will be flowing clockwise. So since we are analyzing the current in the same direction as the resistance, we could say that the potential difference across the resistor is actually going to be the negative, the product of the current and the resistance. One thing to know is the current is going to vary as a function of time because the charge is varying as a function of time. And remember, current is defined as the time rate of change of charge past a point. And now let's look at the potential difference across the capacitor. Potential difference across the capacitor from C to B, well, we use Valley College's quaint, right? When we do that, we would get that potential difference is equal to the charge on the capacitor plates divided by the capacitance. And that takes us from high potential of the positive plate to the low potential of the negative plate. Now, those are our potentials of our three components. Let's apply them. Let's use the cool thing about Kirchhoff's laws is it gives us a set of equations that we could do something with. Kirchhoff's law for voltage, for example, says if we go in a complete loop, starting at point A and ending at point A, the potential difference of that complete loop is equal to the sum of the potential differences across each of our components in our circuit. So the potential from A to B plus potential from B to C plus potential from C to A. And when you go all the way around the circuit, we know that they must sum to 0. So that means some potentials are positive and some potentials are negative. Well, if we were to do this for our circuit, we have the potential from A to B, which is the EMF of the battery, the potential from B to C, which is the potential difference across the resistor, and then the potential from C to A, which, look at what I'm going to do. It is a minus the charge over the capacitance, and that is equal to 0. Now, why do you think I put a minus there? Can anyone tell me? The minus in front of the capacitor's potential. Well, let's look at the capacitor. So when we are working our way around the capacitor, as the capacitor is charged, it is a source of potential. So if you look across the capacitor, and I'm going to just redraw it over here to the right, This is the positive plate. This is the negative plate. Here is our analysis direction. The capacitor is a source of potential. So when we go from the positive plate to the negative plate, we are lowering our potential. The change in potential is negative. Since the change in potential is negative as we go from positive to negative, this potential difference across the capacitor has to be indicated with a negative sign. And that negative sign is important for our circuit. Okay, so we now have Kirchhoff's loop law for voltage. Our goal is to figure out how long it'll take our capacitor to charge. It's initially uncharged. And this equation right here indicates charge as a function of time, but there's nothing with time in it directly, unless you go back to the definition of current. Remember, current is the time rate of change of charge. I am going to add this expression to our equation. So this is now current dq dt times the resistance minus Q over C. And I'll just leave this as a functional symbol here for the charge, because we need to find charge as a function of time ultimately. And this is equal to 0. So our time rate of change of charge, dq dt, that's important because that's going to allow us to find an expression of charge as a function of time. Any questions so far? Okay, so let's look at this expression right here. What I'm going to do is I'm going to isolate my charge terms on one side of the equal sign. So I have dq dt, and here is r as a coefficient, plus Q over C, that's the potential difference across our capacitor, is equal to the EMF of our power supply. So this equation right here is basically saying the power supply is the source of the potentials across our resistor and our capacitor. And so here, our goal is to solve for charge. This right here is called a differential equation. A differential equation is an equation of derivatives. We can't simply divide through by Q or multiply through by time, because certain types of differential equations have certain techniques that we follow in order to successfully solve them. So what we've learned with Math 3B for integration, that's just the beginning to understand how to solve a differential equation. I'm going to take a course of technique that we learned in our Math 4B differential equations course. So this is going to be a review for some of you. But our goal is to use this equation involving that derivative of charge as a function of time, and use it to come up with a single expression for charge as a function of time. To do that, I'm going to just do a little bit more rearranging of this equation. I'm going to divide the equation by the resistance, just to put it in this form. And what we have here, if you were in a differential equations class, they would call this a first order linear non-homogeneous differential equation. And there's a certain way in which you could determine the solution of this equation. This type of equation has two solutions, and we sum those two solutions together as a single solution. the two solutions will have a form. One is called the complementary solution, and one is called the particular solution. Now, what the complementary solution is, the complementary solution is when this differential equation is turned into a homogeneous differential equation by getting rid of this constant that we have there. So when we take this equation and solve it, assuming that that constant is 0, this is called the complementary equation, and we could solve this complementary equation. So what I'm going to do from this step is I am going to separate my time term from my charge term. So I just put the charge term on the other side, separating the two. Now what I'm going to do is I am going to divide, well, this is what I'm going to do. I am going to divide both sides by the Q for our complementary equation. This then becomes 1 over our Q for charge, dQ, is equal to minus 1 over RC. And now I am going to integrate both sides with respect to, oh, and I forgot my dt on this left side. I'm going to integrate both sides with respect to time. When we integrate both sides with respect to time, the left side just becomes the integral of 1 over q dq, and the right side becomes the integral of 1 over rc dt. Now, rc, that product is just a constant. The left side, 1 over q dq, you should recognize that to be the natural log of q. And the right side, we have minus 1 over RC t plus a constant of integration. Instead of using C, I'll just use D to represent our constant of integration. Notice, we are a couple steps closer to expressing charge as a function of time for this complementary equation. Charge is on the left, time is on the right. So what we want to do from here is exponentiate both sides. So in other words, write both sides as exponent of the natural log of e. What we have is e to the natural log of e. The left side just becomes the argument of that natural log. And the right side is just e to the minus 1 over rc t plus your constant of integration, which I am going to rewrite this as g e to the minus 1 over rct. And if you're wondering what happened to the d, I'm just defining g to be equal to e to the d. So in other words, I'm pulling out e to the d as a constant. This gives us part of our solution for the charge on our capacitor, that the charge of our capacitor is equal to some constant of integration, e to the minus 1 over the product of the resistance of the capacitance times time. Here's our time dependence, or at least part of it. Part of our time dependence. Now remember, I said that the charge as a function of time is a combination of this complementary solution that we just found and a particular solution. What a particular solution is Well, let's go ahead and just rewrite our differential equation so I could show you. So what a particular solution is, it's when you have something on the right side of your equality that changes this linear differential equation to what's called a non-homogeneous differential equation. When you take Math 4B, you'll learn that a differential equation in this form, we could guess a solution for the particular equation. Now, I'm going to guess that since the right side of this equal sign is a constant, I'm going to guess that my solution to the particular equation is going to be a constant. So in other words, I am going to guess that our particular solution is going to have a form of a constant. And I'll just call the constant A. So what do we do with that A? We're just saying that the QP is a constant. So if I replace QP with that A, and the A, again, is just a reminder that our particular solution is a constant, well, the derivative of a constant is 0. I'm left with R in the denominator on both sides. They cancel out. And what I'm left with now is that our particular solution, QP, I'll write it like this, is equal to, well, if you look at this on above, this means that our particular solution is just equal to the product of the EMF of our battery and the capacitance of our capacitor. Okay, let's put all of this together. So we said QC was equal to G e to the minus 1 over RCT. We said QP is equal to the product of the EMF of the capacitance. And we are also saying that our total solution is the sum of the particular solution and the complementary solution. So when we write it as the sum of those, we have, here is our particular solution. Here is our complementary solution. And the only thing we have left to do now is determine that constant of integration G. Because we know the EMF of the battery, we know the capacitance of the capacitor, we know the resistance of the resistor. The only thing we don't know is G, and how we're going to find G is we're going to apply our initial value. Remember, we said that at t equals 0, our charge is equal to 0. So let's plug that into this expression right here. At t equals to 0, we're calling that Q naught. We have this expression, e to the minus 0, and we're saying that this is equal to 0. Well, this is saying that the product of the EMF and the capacitance plus our constant of integration is equal to 0. So this initial value allows us to determine our constant of integration. Our constant of integration is equal to minus the product of the potential difference and the capacitance. This means we could now finally write, let's do this. We could finally write an expression for the charge as a function of time. Charge as a function of time is that product of potential difference in capacitance minus the product of potential difference in capacitance, e to the minus 1 over RCT. And I'm going to just express this slightly differently by factoring out the product of the EMF and the capacitance. And remember, Valley College is quaint. EMF is a voltage, capacitance is capacitance. EC, that's our charge. And this is equal to 1 minus e to the minus 1 over RCT. This is the result that you need to know. We just derived it. I'm not going to make you derive this, but you do need to know this result. This result right here gives us the charge on a capacitor in a charging RC series circuit. So we'll say in a charging RC series circuit.